Alright, so for this, we know the whole charge of the whole thing is Q. So at each individual point, because when we're taking the integral, we're just sweeping something from here to here. We're just sweeping it. So at each of those individual points that we're trying to look at each of them, the charge, so is going to be, like if we're looking at just ignoring everything else, it's just going to be the field equation for right now, right? Okay, so our charge at any of those given points, and once we sum these up, that's taking the integral, that's our summation. So the charge at any point is some fraction of this final charge Q. So it's going to be that over Q. But we have to find out what fraction of Q that is. So now if we're looking at what fraction of the charge that we are looking at each point, what we need is what fraction of the whole rod are we looking at each of our infinitesimally small pieces, right? So the length, any arc length, is going to be the theta times the radius. So in this, it's given radius is a constant, just with the capital R, but it's also given those two thetas there, that's going to give us the whole arc length of our thing. So the whole part is just going to be 2 theta r. That's going to be like our Q equivalent, right? So for every 2 theta r, there's Q charge. And then for each of our like infinitesimally small points, right? So like if these are super close together, the thing is the angle between them, and those are not straight lines, but the angle between them, that's like so this is like a constant theta. Like if I'm going to use alpha for what's going to move, it's going to be like a d alpha. That's our d alpha. That's what's approaching 0 as it's getting super duper small. And that's still times that same radius. So this is our piece. This is the piece that's there, and this is the whole. So what fraction that we have is r d alpha over 2 theta r, and it's that fraction of Q. So like this is what fraction of the whole that we have. So if you multiply that times Q, I know I said put it over Q, but this is going to be equal to our lambda over Q. So you multiply it out to get this lambda, right? Because our lambda is the charge per unit length. So that's what we're finding with this. So if we multiply both Q, that's just going to give us our lambda. So we have this times Q. Okay, and I did spoil the ending a little bit by putting this in terms of d alpha, because I mean usually you'd like dl, but since what we're doing here, we're not sweeping across a straight line like that. It's not the change in length really. We're going to be sweeping like the whole semicircle, so it's going to be here. Our theta is what's going to be changing, sweeping this. So that's why I did d alpha, or not theta, alpha is going to be changing, but theta is just angle variable. You know what I'm talking about, it's fine. So we have our charge up there, and that's going to be acting at a radius. Oh, and also these r's can cancel because on the top of my, and then that's still over the radius, r squared, because that radius doesn't change. And that's also multiplied by ke technically, but it's just k. So because that radius doesn't change for that whole entire thing, because if you're doing like length, then it would be harder to finagle. But yeah, the radius doesn't change that whole time. It's constant, so we can just do that. Alright, so now we have this simplified equation over here. But now it needs that direction, that r hat that we have to multiply in. So looking at this, our line of symmetry, it's here. So if you think about it, this much is acting on it this way, or sorry, this way, and this much on this side is acting on it this way. So they're going to be acting in equal and opposite directions. So in the x direction on this axis, since it's this way a certain amount and this way that same amount, are going to cancel. So the x direction actually would cancel to 0, right? So really what we're looking for is going to be that y direction going this way. And based on the angles that we have, since it's not an outside angle, it's going to be like cosine. So we're just going to find, right now, just to look at it, we're going to find this half of it, right? I'm just going to look from here to here, however, whatever it is. And I'm only looking at this half of it, and then just multiply the final answer by 2, because they're going to be acting in the same way, just in different directions. But the y components are going to be the same, so you can just add them together at the end, or just multiply the answer by 2. So that's what I'm doing with that. All right, so we have our theta inside here, but I already said that our alpha is where it's going to be changing, so that's like here to here, or here to here, like that's what we're looking for. So if we're looking for the y direction, that's going to be adjacent. I'll draw it down here too. It's going to be this in this y direction. That's going to be adjacent to this angle. But if our alpha is starting over here, the angle that we're looking to be adjacent to, like this hypotenuse, is what we're trying to get the component of. This is our y direction, x direction. All right, we're looking for this angle here that we're getting the adjacent of. So that's going to be our big angle theta minus alpha. Since it's the adjacent sign, it's going to be the cosine of theta minus alpha. So with our directional bit, this is our r hat. That doesn't get canceled because the sign whatever would have just gotten canceled. And our direct magnitude bit, we can do our final answer. It's just going to be, I'm just going to pull some of the stuff out of the integral as well as I go, because some of it are just constants. So it's like 2ke. I'm multiplying the whole thing by 2, remember, because there's 2 sides. I'm just only integrating 1 because it's an easier integral to do. And that's between 0, because we're starting like our 0 theta, or our 0 alpha's over here, and that's going between 0 and theta. And 0 to theta of q d alpha over 2 theta r squared cosine of theta minus alpha. Right? So technically I can pull out a few more things in here because q is a constant, this 2 is also a constant, this theta is a constant, this r squared is a constant. So it's going to be 2ke q over 2, so this is going to cancel as well, theta r squared, integral of, from 0 to theta, cosine of theta minus alpha with respect to alpha. And this is the integral that you're solving and plugging into to get your final answer. So when you integrate this, if I just ignore this mess of a coefficient off to the side, it's going to be, when you integrate cosine, it's sine of theta minus alpha. But since we're taking the derivative with respect to alpha, you have to like de-chain rule. Oh, my mac and cheese is done. We'll come back to that. If you're taking the derivative, you're multiplying by the derivative of this. And since this is a constant, it's just going to be -1. But since this isn't negative, the negative sign just goes here. So this is our integral here, and we're evaluating that from 0 to theta.